So hello, and in this video me and my colleague are going to give you a short overview about a recent reinforcement learning research paper. The title of the paper is Diversity is All You Need, Learning Skills Without a Reward Function. So let's start. So let's briefly introduce traditional reinforcement learning. So reinforcement learning has proven to be quite effective in training agents to perform a wide range of tasks. They have proven to be particularly effective in learning reward-driven skills. Now, in order to do that, they need to be provided a reward function of some sort. The reward function is basically the parameter that guides the learning process. The goal of the agent is typically to maximize said reward function. The bigger the reward function, the better it is, right? And in this paper, the authors propose a new approach to reinforcement learning that doesn't utilize reward function as the basis of the training, but instead utilizes diversity. So why exactly would we want to do that? Now, as it turns out, reward functions actually have quite a few problems. One of those problems is sparsity. Now, if the environments are sparse and also the reward functions are sparse, we would effectively have little to no reward during our training until the agent just randomly stumbles upon a goal state. Furthermore, if the environment is complex, it can also be quite difficult to define an appropriate reward function that elicits the desired behavior that we want from the agent. Also, when given an unfamiliar environment, it is difficult to define what actions an agent should be able to learn from. So, in order to counteract and mitigate some of these issues, the authors propose a learning method without supervision. And they argued that learning without supervision would help address some of these challenges that a traditional supervised learning model with a reward function presents. So the algorithm is called Diversity is All You Need. So again, an unsupervised reinforcement learning model consists of two stages. So the first one is the unsupervised exploration stage. And in this stage, the agent would simply learn different skills, and then those skills would then be used in order to maximize the reward in a follow-up supervised stage. So in the second stage of the algorithm, a reward would still be used. And skills are learned without any prior knowledge of the environment, hence they in theory should be able to be used in many different tasks. So a little bit about the methodology. So we train here multiple skills at once. And these skills are then used in order to produce discriminable states. And in order to increase the discriminability of our skills, we also train a discriminator as well as training our skills. On top of being discriminable, we want the skills to have a high degree of entropy, or in short, the skills should basically just be as random as possible. And we want our skills to produce diverse states. So diversity is, again, the basis of training, not the reward. So this is a graph about how the algorithm actually looks like. So basically, we sample a skill from a given distribution. A skill is actually quite similar to a policy in a traditional reinforcement learning model. It is used to determine an action for a given state. That action would then be used by the environment in order to produce a follow-up state. And then here we would feed that follow-up state to our discriminator. We would train it, and it then would try to estimate the skill that was used to get to that follow-up state. And this process is then just repeated multiple times. So in order to be useful, our skills should be able to dictate the states. Furthermore, we want to use states and not actions in order to distinguish between our skills. And in the paper, the authors give an example of a robot grasping a cup. And as an outside observer, unless the cup moves, we would not be able to basically tell what was the amount of force that was applied to the given cup. So again, we want to use states, not actions, in order to distinguish between our skills. So on top of discriminability, we also want our states to be as distinct as possible, hence why randomness is introduced in the initial exploration stage. And we want both a high entropy and discriminability, because if we combine both of them, then our skills should be able to explore a part of the state space that is as far away from other skills as possible. And all of that increases the diversity of our model. So for the training, we use a soft actor critic, which is learning a policy that is conditioned on a latent variable. And the soft actor critic is basically just used to maximize the entropy over the actions. And then during the initial first stage of the algorithm, we sample skills from a categorical distribution. We use those skills in order to define actions for a given state. The agent is then rewarded for visiting states that are easy to discriminate. And on top of training our skills, we also want to train the discriminator at every single episode. And this discriminator is basically used to increase the discriminability of our states or of our skills. And as we saw in the graph a couple of slides ago, the discriminator has no input about what skill or what action was used in a given state. It just has the follow-up state, and it tries to estimate what skill was used to get to that follow-up state.
And now we are coming to some results of this paper. We'll start with a short overview. In order to evaluate their approach and compare it to some prior work, they decided to conduct a few experiments. They started by analyzing the skills. They analyzed their skills first on some simple tasks and then some more complex tasks. So on tasks of increasing complexity, they are also able to show that their algorithm can cope with some problematic behavior that can be found in some previous work and previous algorithms. In the end, we will be able to see that skills that their algorithm is able to learn can be used for some downstream tasks. In order to conduct these experiments, they use some famous training environments like half cheetah, ant, hopper, mountain car continuous, and inverted pendulum. And now we're coming to training results. With the first experiment, they wanted to show which skills their algorithm is able to learn. In order to show that, they studied the skills on tasks from 2 degrees of freedom to 111 degrees of freedom, like ant locomotion, so from very simple tasks to some more complex tasks. They start with some simple tasks like agent in 2D environment can change its position, x and y position, and in this environment, agent was able to learn 6 different skills. After that, they tested some more complex environments like car mounting and virtual pendulum, and in the end, they tested also with the really complex environments, control tasks like half cheetah, hopper, and ant. And what they concluded is that agent is not only able to solve the task, but it's also able to solve tasks with multiple distinct skills and without any reward. Some skills that the agent learned were walking, jumping, doing flips, balancing, hopping forward, and diving. And now we're coming to some more results. What they concluded was that skills become increasingly diverse through the training. Some skills correspond small task reward and other large task reward. This is the case of because this is fairly natural, because we are dealing with a function, with the algorithm which does not have any reward function. They were able to show that their algorithm is robust to initialization. They tested with 5 random seeds, and the environment that they used by this experiment was car mounting and virtual pendulum. They also wanted to show that although their algorithm favors skills that do not overlap, it's not limited to learning skills that visit entirely disjoint sets of states. In order to conduct that, they did experiment with the hallway, where agent starts in the hallway and the goal is to exit the hallway to the large room at the end of the hallway. Because most of the agents are incentivized to maximize their cumulative reward, they may take actions that initially give no reward to reach states that eventually give high reward. In this environment, diversity is all you need. Learn skills that exit the hallway to make them mutually distinguishable. And now we're coming to to the point where they compare their prior work with some prior algorithms. First, they compared this with variational intrinsic control from 2016. The big difference between these two algorithms is that they are not using prior, they are not learning the prior of the. In their experiments, they showed that variational intrusive control is suffering because of this. It samples more diverse skills more frequently, and only those skills will receive training signal to improve. Evaluation and comparison, they did evaluation comparison on half cheetah. In the graph which we can see that effective number of skills throughout the training. And this shows that variational intrusive control quickly converges to only samples of handful skills, while diversity is all you need fixes distribution over skills, which allows us to discover more diverse skills. They also compare the algorithm to variational information maximizing exploration, which is basically the algorithm that combines ideas from variational inference and reinforcement learning to address the exploitation trade-off in reinforcement learning. But we will find more about that later in the slide. And now we are coming to application of diversity is all you need to other RL algorithms. The fact that we can discover diverse skills without reward function creates a building block for many problems in RL. Diversity is all you need can be used as unsupervised pre-training for more simple, efficient fine-tuning of task-specific policies. After learning with this algorithm without supervision, some, for example, task-agnostic skills, it can quickly adapt these skills to solve a desired task. It can also be used to maximize task reward. We take just the skill with the highest reward for each benchmark task and further fine-tune this skill using the task-specific reward function. Now about hierarchical RL. In hierarchical RL, it decomposes a complex task into motion primitives, and this can lead to many problems like each motion primitive reduces to a single action. These problems can be solved using diversity is all you need, because it discovers diverse task-agnostic skills. So this approach algorithm can be used for hierarchical RL. We just need to do some extension, simple extension, and we just need to add some meta controller, which is basically controlling which skill to execute for next cast steps. The meta controller has the same observation space as the skills. They showed that their algorithm outperforms baselines on two challenging tasks by doing the comparison to algorithm called variational information maximizing exploration. And they showed by doing comparison that the reward increased with the number of skills. To ensure that those goals were not just cherry-picked, they sampled 25 goals evenly from the state space and evaluated each random seed on all goals. And in the end, they concluded that variational information maximizing exploration significantly underperforms even the best random seed. And now we are coming to some more applications of diversity so we need to RL algorithms. So they applied hierarchical algorithms on two challenging simulated robotic environments like cheetah hurdle and edge navigation. In cheetah hurdle, cheetah has to not only move but also jump over some hurdles. And they were able to show that their algorithm outperforms state-of-the-art on policy, trust region policy optimization. And also, as already stated, variational information maximum exploration. They were also able to show that their algorithm scales the task with more than 100 dimensions, but not only that it scales to do the task with more than 100 dimensions, they were also able with some simple tweaks and simple adjustment able to adjust their algorithm to be biased towards discovering particular type of skills. And in the end, they were able to show that their algorithm can be used to imitate an expert. One use case is where human manually controls the agent to complete a task that we would like to automate. Simply replaying the human's actions fails in stochastic environments, cases where closed-loop control is necessary. And for those who are interested, those experiments and videos of those experiments like cheetah moving, learning how to move forward, backwards, jumping, and all other stuff can be seen on the web page below, on the link below. And now we are coming to the conclusion of this paper. In this paper, we were able to see a new approach for learning skills without a reward function. Diversity is all you need not only provides a simple alternative to traditional RL models, making it suitable for a wide range of tasks, but this algorithm is also able to solve tasks often without any task reward. It showed promising results in various domains, demonstrating its potential for practical application, just like we saw with the hierarchical RL, and imitating expert, and all other cases, diversity is all you need has the potential to make RL more accessible to a wider range of researchers. It is still an emerging field, so further research is required in order to fully understand its limitations. And that was all from us today. Thank you for your attention.